To the organizers for inviting me to come here. I'm having fun. My title today is, as you see, late-time behavior of homogeneous solutions to the Einstein-Vlasov system. We'll start with one or two general remarks. As I think most of you know, the Einstein-Vlasov system describes self-gravitating collisionless matter. Of course, you can also describe self-gravitating collisionless matter using the Vlasov-Poisson system, but the characteristic thing about the Einstein-Vlasov system is that it is a fully relativistic generalization of the Vlasov-Poisson system. Now, this, we've already seen it in Håkon's talk. This is a complicated system of equations in general, and it's not so easy to prove things about its solutions, and for this reason it's a good idea to make symmetry assumptions to get simpler problems which are easier to attack. And a very strong symmetry assumption is spatial homogeneity. So this is, roughly speaking, where you assume that everything does not depend on space. I'll explain later more precisely what it means, but basically you get rid of the spatial variables and then you obtain a much simplified problem. Nevertheless, it's not too simple. You still obtain very varied dynamics for these solutions which are spatially homogeneous. This would not be the case for Vlasov-Poisson or Vlasov-Maxwell, but for Einstein-Vlasov, and I tend to put Einstein first because somehow studying these equations you learn that the Einstein equations seem to be playing the dominant role. In the case of Einstein-Vlasov, there's still plenty of dynamics already in this spatially homogeneous case. So, I've already said this, that the basic idea is that you should eliminate the spatial dependence, and the formal definition is that you assume that the solution is invariant under a suitable Lie group G. So let me start with a three-dimensional Lie group. This could be any three-dimensional Lie group in this context. And so I will sort of write down equations starting from this Lie group. So the first thing is, in order to coordinatize objects on the Lie group, I introduce a left invariant basis of one forms. And if I do so, then I can write down a metric of the following form. So here, this is supposed to be the space-time metric. It has a time part, which is just trivial minus dt squared. And then the other part is obtained by taking the products of the one forms and then taking linear combinations of these with coefficients which depend only on time. So in the end, these theta I are objects that you put in at the beginning, and they are non-dynamical, and all the dynamics of the geometry is contained in these metric coefficients which only depend on t. So for that reason, in this situation, the Einstein equations reduce to ordinary differential equations because the objects describing the geometry only depend on t. So that's the one major simplification. Now let me just introduce some notation which is typical in general relativity. So if I write Gij with upper indices, this denotes the inverse of Gij with lower indices, and I introduce an object called Kij, which is just like the time derivative of Gij scaled with a certain factor. Geometrically, if you imagine that this is the space-time metric, then you can look at the hypersurfaces t equals constant, and they have an induced metric, which is just given by this Gij of t, and they have a second fundamental form, which is this Kij of t. So that's what these objects mean geometrically. Also, we have this convention that people in relativity like to raise and lower indices using the metric, so that, for instance, if you take k and you multiply it by g and you sum on the repeated index, you get an object which you denote by k with one upper index and one lower index. So it may well be that in formulae I write down later on, I've moved indices without mentioning it explicitly, but if you see objects with indices in different places, then they are related by this kind of process here. Of course, you don't need to understand a lot of details. Okay, so here I'm going to be talking about the Vlasov equation, and of course, as always with the Vlasov equation, we have a basic unknown describing the matter, which is a distribution function, f, and this distribution function in this case depends on time, and it depends on the velocity variable speed. It does not depend on spatial variables. That's the key thing about spatial homogeneity. These velocity variables satisfy a mass shell relation, which allows us to, so in general we actually have 4 components of V, labeled 0, 1, 2, 3, and these, the I here are just the spatial ones, and we can calculate the last one, V naught, by using this mass shell relation. Now, an important input which comes from the Lie group is the following. So I started with these left invariant 1 forms. This basis of 1 forms is a dual basis of vector fields, and this I call EI. And now on the Lie group, if I take the Lie bracket of these 2 vector fields, EI and EJ, then I get something which I can express as a linear combination of the E's again, and this gives me some coefficients C, K, I, J, which are constants. These are the structure constants of the Lie algebra. And these structure constants then come into the expression for the Vlasov equation. Using the structure constants and the metric coefficients, we can define the rotation coefficients as follows. So these rotation coefficients are like the components of a connection on a certain basis, and they will come up in the Vlasov equation. So this is, here's a purely algebraic expression. And then we have the Ricci curvature tensor, and I'm not going to write down the explicit form because it's too complicated to be very useful for you now. I just state that it's a rational function of these coefficients Gij and Ckij. So in particular, it's some kind of algebraic expression. Okay, so now having introduced all these preliminaries, I can go to the basic equations. First, the Einstein evolution equations, which I've written down in first order form. The first equation here is just rewriting the definition of K, and this gives me an evolution equation for the metric G. And the real dynamical Einstein equation is the evolution equation for K, which looks as follows. And what do I need to explain here? Well, here is the Ricci tensor, which I introduced before, with the second fundamental form. And these objects with T's, these are components of the energy momentum tensor, which also occurred in the last talk. And one other element which wasn't in the last talk is this lambda as a constant, the so-called cosmological constant. And as we will see, this cosmological constant makes a big difference to the sign of the cosmological constant makes a big difference to the dynamics. So those are the Einstein evolution equations in this situation, and as you see, these are ordinary differential equations. We only have time derivatives, nothing else. In the case of the Einstein equations, we may not give initial data theory. There are some constraint equations. So this is similar to what you have for the Maxwell equations, that you have divergence-free conditions on the initial data, or conditions on the divergence. In the Einstein case, there are some more complicated constraint equations which the data must satisfy. And I think the one object which has not yet been defined is this R without any indices, and this is the trace of the Ricci with the metric. And lambda is the cosmological constant. Okay, so those are the basic equations for the geometry, and these we now want to couple to an equation for the distribution function. Well, first I have to tell you what the energy momentum tensor is. So if I have the distribution function f, then the energy momentum tensor is defined as follows. So the energy momentum tensor T has indices which run from 0 to 3. From 0 to 3. So the Latin indices, like this one, they run from 1 to 3, and the zeros are either explicitly. So I have oops, I have here the 0, 0 term, the 0 spatial, and the spatial spatial component, and then to them I also give some other alternative names. And here are the expressions. So you see in all cases that what happens is that you take the distribution function, you multiply by some weight which varies with the different components, and then you integrate in the velocity variable. So this gives you something that only depends on time, which is what you need, because the other objects in the Einstein equations in this case also only depend on time. And then last but not least we have the Vlasov equation. So here we have the time derivative. There are no spatial derivatives because f is not dependent on spatial variables, and we have a term containing the velocity variables. And in this last term we see the rotation coefficients, which I introduced before. And what exactly these rotation coefficients are depends on the Lie group you've chosen, because the rotation coefficients depend on the structure constants of the Lie algebra, and those depend on which Lie group you've chosen. So in a sense you could say the problem that I'm describing here is not just one problem, but it's a whole family of problems depending on which Lie group is chosen. Okay, so the Lie groups can be classified. In fact, they were classified by Bianchi in the middle of the 1890s. And in fact, we're not really interested in distinguishing between a group and its universal cover, and the universal cover is uniquely determined by the Lie algebra, so basically it's only Lie algebra that is important. And what Bianchi did was he classified all the three-dimensional Lie algebras. I should maybe have said here three-dimensional, so I'm interested in that case. Actually, I discovered not so long ago that the four-dimensional Lie algebras were classified in 1905 by Fubini, which I wouldn't have expected to find him in that context. Anyway, I'm interested in the three-dimensional case here. So this was Bianchi, and Bianchi made a list from Roman 1 to 9, and this notation is still used by relativists to this day, so I will also use it here. I just thought I would give you a little menu with a few of the groups. There are many different kinds, and on this slide I'm just telling you what a few of them are. So type 1 is the simplest, it's a behaviour. Type 2 is the Heisenberg group. Type 6-0 is the isometry group of the two-dimensional Minkowski space. So if you take the R2 with a Lorentz metric with just components 1, 0, minus 1, then its isometry group gives you this 6-0. Now I owe you an explanation what the 0 means. So the point is that for most of the Bianchi types, one Bianchi type means one isomorphism class of the algebras. But for types 6 and 7, it's actually a one-parameter family of isomorphism classes, or if you prefer, a one-parameter family of non-isomorphic Lie algebras, so you get a parameter. And this 0 here means that this parameter has been set to 0 in the case that I'm discussing. Then another example is type 7-0 is the isometry group of two-dimensional Euclidean space. Type 8 is SL2R, type 9 is SU2, discussed examples, and the other Lie groups or Lie algebras are less familiar, or maybe not familiar at all. Just one other remark is that not all spatially homogeneous models are Bianchi models. There is one exception, which are the so-called Kantowski-Sachs models. And in the Kantowski-Sachs case, what you have is that the spatial geometry is the two-sphere across the real numbers, and this manifold has a four-dimensional isometry group, and that four-dimensional isometry group has no three-dimensional transitive subgroup. So therefore, we can't use just a three-dimensional group for Kantowski-Sachs. We are forced to go to the four-dimensional case. But this is just a side remark. I won't say very much about the Kantowski-Sachs case. Okay, so the question that we're interested in is we want to look at the Cauchy problem for this system. giving initial data at some time t equals t0. The data which we have to give are the metric at time t0, the second fundamental form at time t0, the distribution function at time t0, and these are supposed implicitly to satisfy the constraints which I wrote down before. And I make one extra assumption here, which is that if I take the trace of the second fundamental form with the metric, then this should be less than 0. Now, if it happened that this object was greater than 0, I could make it less than 0 by replacing t by minus t. So this here has to do with making a choice at time direction. These solutions of the Einstein equations are typically used to describe the evolution of the universe. And you know, in general, the picture we have is that our universe is expanding, and an expanding universe corresponds to having this negative sign. If I had the positive sign, it would mean a contracting universe. So given that we observe that our universe is expanding, it's natural to make this choice. Now, it turns out that there is a big difference between, on the one hand, types 1 to 8, and on the other hand, type 9. So if you start with initial data which satisfies this condition, then it turns out that for types 1 to 8, the solution exists globally in the future. This is not so hard to prove. And this is what I will call a forever expanding cosmological model. In fact, in this case, this object here stays negative for all times. So that's the justification for calling it forever expanding, since having this object here negative means expanding, and so if this holds at all times, it's forever expanding. Things look very different for type 9. For type 9, you find that this same quantity actually, even if it starts negative, will become positive after finite time, and then it will go to plus infinity in finite time. At least if the cosmological constant is 0. If the cosmological constant is non-zero, this may be different. But for the case lambda equals 0, we get this statement. So for this reason, in this talk, I'm mainly going to be interested in late time behavior. So I will concentrate almost entirely on this case, types 1 to 8, because type 9 has no late time behavior. There's no t tends to infinity regime. I just mentioned in passing, Kartowski-Sachs is like type 9, so it also expands and then recollapses the second singularity. So this is another reason why Kartowski-Sachs will not play a big role in what I have to say here. Okay, so now it turns out that if we make the assumption that the cosmological constant lambda is positive, then this simplifies the problem a lot. Let me just introduce some further notation. I define a constant h0 to be the square root of lambda over 3, and I define an object sigma to be the trace-free part of the second fundamental form. This object here is sometimes called the shear in cosmology. And now, long time ago, 1983, Bob Wald showed some statements about the asymptotics of this kind of solution. So what he showed was that if you have a solution which exists for all time in the future, then certain asymptotic statements are true. Firstly, this object here, which is actually called the mean curvature, will converge to this constant 3h0, and moreover, the shear, or the square of the shear, will decay exponentially as t tends to infinity. Now, I should point out that in Wald's paper he said nothing about Vlasov, and in fact this was not confined to Vlasov. So this was a statement about the Einstein equations coupled to reasonable matter, which may be many different things, Vlasov or fluid or something else. So this was, in a way, rather weak assumptions. He only assumed things like positivity of energy of the matter, and from this he was able to get these statements on the asymptotics, under the assumption that the cosmological constant is positive. Now the interpretation of these statements are, so the first one we can interpret as being exponential expansion. We will see this in more detail later, but basically this object here is like the inverse of g times the time derivative of g. So in other words, it's the logarithmic derivative of g, and if the logarithmic derivative is becoming constant, then the evolution is becoming exponential. So this is why this statement here can be interpreted in terms of exponential expansion. And the second statement is a statement that the geometry is becoming isotropic, because somehow the sigma is measuring the deviation from isotropy of this object A. Now, that was for general matter, let's say, but in particular, the assumptions on the matter are satisfied by Vlasov. So this theorem of Wald applies to Einstein-Vlasov. On the other hand, if you make the specific choice of Vlasov, you can go much further. And this was done in 2004 by Hai-Young Lee, and she proved detailed asymptotics of the situation. Now I want to say something about that. So in particular, she showed something very explicit about exponential expansion. So you see here that the metric as a function of t looks like a fixed metric, so not depending on t, times an exponential factor. So you get this exponential expansion with a particular exponent. Moreover, in this work it was shown that the shear decays exponentially. So this is now a little bit different from what I had before, because this says that the square of the shear as measured by the metric decays exponentially. This actually shows that the shear itself decays exponentially, which is a somewhat stronger statement. So in this way, we actually get, in a way, complete information on the leading terms in the asymptotics for the geometric variables. I mean, I just said all of this. I mean, this is really the leading term. So it's not just that this is a one-sided diamond. This is really the leading term. The other thing is, of course, we would like to know something about what happens to the solution of the Vlasov equation. And there are also statements. So the one is that the component of the energy momentum tensor rho, which is the energy density, this is T naught naught, this decays like at a certain exponential rate, and moreover, you can show that the other components decay faster. So rho is the component that decays slowest. So both of the other, or all of the other components, if you divide them by rho, the result decays. And so these statements here can be interpreted in a certain way, which I want to explain now. So the language is to say that the solution approaches untilted dust. So what do I mean by untilted dust? Well, firstly, what is dust? Dust means that if I replace the smooth distribution function by a certain object which contains a Dirac delta in the following way, then so what I do is I take a rho depending on t times a delta of v minus some v depending on t. So there's some particular velocity at each time, which is the only velocity which is represented in the distribution function. And this velocity v is known as tilt. So if you just formally substitute this into the Einstein equations, or also into the Vlasov equation, then you get a model which is well known in general relativity, and which is called Einstein dust. So this is a kind of limiting case of Einstein-Vlasov. Very often, also when I was in Seoul recently, I make propaganda against dust, and I say it's a bad matter model, don't touch it. But in this case, when it's spatially homogeneous, it's okay. So it's only when there are inhomogeneities that it tends to form horrible singularities, and it's pathological and so on, but today it's okay. So now the point is that these statements here are really saying that the solution of the Vlasov equation is looking more and more like dust. Because for dust, this Ji will be 0 and the Sij will also be 0. But rho will not be 0. So it's sort of natural that dust corresponds to these ratios here going to 0. Moreover, the dust, untilted dust. So for untilted dust, these two objects will be zero. So for that reason, I described this as saying that the solution is approaching untilted dust. So that's what I wanted to say about the case of positive cosmological constant, and basically we have a pretty complete picture. So anything we would like to know about the asymptotics in this case, we can get from what is already known and proved. Before I leave the case lambda positive, I would just like to mention that there are a couple of more general results which are not homogeneous. So really, lambda positive is a lot easier than lambda equals 0, and for this reason there have been some results obtained even in the inhomogeneous case. I will mention a couple of those. So there was one result by Les Chapenda and myself where we looked at inhomogeneous solutions with a certain kind of symmetry, which is called plane symmetry. I won't go into details here. And what we found was that the asymptotics look very similar to what is known from a homogeneous case. There's also some work by Hans Ringström, which is not yet published, but he's writing a thick book on it, I believe, where he actually proves a small wave global existence result without symmetry. So actually, when you have a positive cosmological constant, it's such an advantage that you can hope to really go a long way in looking at inhomogeneous solutions. In any case, that's not my subject today. That was only just to put it in context a little bit. Now I want to come back to the case lambda equals 0, because this is a lot more complicated. So we've seen, I've explained that for lambda positive, the solutions approach untilted dust. So the question is, does this also happen for lambda is equal to 0? The first statement is no counterexample is known, at least not to me. So maybe we can hope to try and prove this. Also, there are partial positive results around on this question, and I will explain something about those now. So one case which is particularly simple is the so-called LRS case. This LRS stands for locally rotationally symmetric. So in the LRS case, you have not only a three-dimensional symmetry group, as in Bianchi in general, you have a four-dimensional symmetry group, and the isosymmetry acts as a rotation about a given point, so that's why it's called locally rotationally symmetric. And in this particular case, it turns out that you can reduce the Einstein-Vlasov system to an ODE system. This you cannot do in general for even homogeneous solutions. Why can you reduce it to an ODE system? Well, I should say, before I say that, let me first say this ODE system is not explicit. You only know you can reduce it to an ODE system, and you have qualitative information about the coefficients of the ODEs, but you don't have really explicit expressions. In any case, you can reduce it to an ODE system, which is a big advantage. And the reason for this is, well, we've seen a couple of times today already, whenever we have a symmetry, we get a conserved quantity for the characteristics. And in the case of Bianchi, we have at least three symmetries, so we get three conserved quantities. So what we could try to do is we could say, okay, let's take f to be a function of those conserved quantities. However, there's a problem. Not all of these conserved quantities preserve the symmetry. So when we build this thing, we test to see if it's invariant under the symmetry, and it's not in general. And this has to do with the non-commutativity of the group. So if you want to, so there's an obstacle here, and it turns out that you can overcome this obstacle if you have a fourth symmetry. So if you're in the LRS case. And in that way, you have so many conserved quantities that you can reduce everything to an ODE system. Otherwise, and if the group is not abelian, you can't. Okay, so I'm still now thinking about the LRS case, where you have this ODE possibility, and then it turns out that you can see the following. So firstly, in this question I posed, we are comparing Vlasov with dust. So first we should ask what happens for dust. And there it is known that in Bianchi types 1, 2, and 3, there is a unique self-similar dust solution. Just, yeah, self-similar dust solution. And it turns out that at late times, this self-similar dust solution is LRS, and it's an attractor at late times for all dust solutions, homogeneous dust solutions. And now it turns out that it's also a model for the late time behavior of LRS solutions in the Vlasov case. So if we have this LRS assumption, we can indeed prove that the answer to the question I asked is yes. And this was done mainly in a paper by Klaus Udler and myself. And then, well, Bianchi 3 has a certain subtlety. It's a bit more difficult than types 1 and 2. It needs a center manifold analysis, which I did in this later paper. So these LRS types 1, 2, and 3, they're basically well understood. And the answer is we find untilted dust asymptotics in all these cases. So this supports the idea that this might be the general behavior. But now what I want to do is to try to say, well, can we go beyond this ODE case? In the case that we really get left with a system of integral differential equations, or partial differential equations coupled to integrals, can we still say something? Now, there's another kind of symmetry assumption which you can make within Bianchi type 1. So remember, Bianchi type 1 is the case where the Lie group is abelian, which is the simplest kind of symmetry. And one useful assumption you can make here is that you assume that F is invariant under reflections, where you simultaneously reflect two of the components. You might ask, why do I simultaneously reflect two? Why do I not just do one? That's actually, this would not be so important for type 1, but for the more general Bianchi types, they are not consistent with doing reflections where you only reverse one of the velocity components, but they are consistent in many cases with reversing two of them simultaneously. So that's the motivation. And so now it turns out that in the reflection symmetric case, so when you have invariance of the solutions under these kinds of reflections, then again you can prove that you get untilted dust asymptotics. The next question you might ask then is, what about general solutions of type 1, which are not necessarily reflection symmetric? And this has been investigated recently by my student, Ernesto Munguesa, and he has been able to show that in fact for general solutions of type 1 you also get untilted dust asymptotics. So he showed, well, for small data. So for small data, he gets convergence to a self-similar dust solution, and he's able to prove isocialization. So basically you get qualitatively the same kind of statements as you had for the case of lambda positive. I won't say much about the proof, except that its structure is that of a bootstrap argument. So you somehow have an idea how the limiting solution should look, and then you introduce some quantities which measure the difference of various quantities from their homogeneous values, and then you apply a bootstrap argument to that. Now, one sub-case of the Bianchi models, which is of particular importance, is what is called Bianchi class A. Bianchi class A corresponds to the case that the trace of the structure constants are zero. This is the property that you have a unimodular Lie algebra. And it turns out that in this case, you can actually make your Lie group compact by factoring it out by a discrete group. And this is basically the only case you can do this without assuming even more symmetry. So since for certain applications you'd like to have a model which is spatially compact, you are particularly interested in this case of Bianchi class A. On the other hand, Bianchi class A is also a case which is relatively tractable from a purely mathematical standpoint. So which are the Bianchi types of class A? They're the ones which I've listed here. In fact, you may remember that those are the ones where I told you which groups these types are. And now it turns out that if you ask about what happens with dust solutions, then, well, the dust solutions in these cases are well understood. So type 9 we're not interested in because we don't get late time behaviour of any kind. Types 1 and 2 I've already explained. Something about them that types 1 and 2 are actually, you get self-similar solutions, and the more general solutions are asymptotically self-similar. However, there is no self-similarity in types 7, 0, and 8, so they are more difficult to handle. Instead of self-similarity, what you get is persistent oscillations. So asymptotic self-similarity means that certain dimensionless quantities are converging to a constant value. In these cases, they're not converging to a constant value, they're just oscillating forever. So this makes the analysis definitely more complicated. The situation at the moment is that for types 2 and 6 naught, NumGuessr already has some preliminary results, and I would be hopeful that it's possible to actually handle these cases by the types of arguments that he uses. These other two types are likely to be significantly more difficult. Okay. So I would like to just mention one or two other related results here. One thing is that a positive lambda can be replaced by a nonlinear scalar field. So you may have heard or read about in the newspaper dark energy, and dark energy is a kind of strange matter which has an effect a bit like a positive cosmological constant. So in this context, we can also make some models for dark energy. So what this means is that we now replace the energy momentum tensor of the Vlasov field by a sum of two parts. We have a Vlasov part, which looks as it looked before, and we have another piece which is built out of a scalar field. And the scalar field is a solution of a nonlinear wave equation, which looks as follows. So this is a real value. Oops. This is the effect of dark energy. Thanks. Now we get this nonlinear, well, it's a nonlinear wave equation, but in the homogeneous case, of course, it's a nonlinear ODE. And phi is a real valued function depending on time. And this d of phi is some smooth function which you are in principle allowed to choose. And in order to get a similar type of asymptotics to the case of a cosmological constant, so now I'm thinking about throwing away the cosmological constant, or putting the cosmological constant to 0, but adding new matter, defined by the scalar field. And what happens here is, if you choose the right kind of potential V, you can mimic the effect of a positive lambda. And this was done, for instance, by Hyrum Lee, where she took an exponential potential. This is also something which is very common in the physics literature. However, it's not just any exponential. You must choose an exponential which does not fall off too fast. Because if it falls off too fast, then you don't get this effect. I mean, you could think of the cosmological constant as being like a constant potential, in a sense. So let's imagine this is picture of lambda, and the other case is you have some exponential fall-off. And but this, it shouldn't be too fast, this fall-off. The exponent shouldn't be too negative, otherwise it doesn't work. And in fact, this restriction here in this work is sharp. So if you go beyond root 2, it fails. What you can also do, and what I did some years ago, was to do intermediate cases. So suppose you have some suitable kind of potential which is in between an exponential one and a constant one. You can also prove similar results. Similar results means that we can control the asymptotics, and the qualitative nature of the asymptotics is quite similar to the case with positive cosmological constant. In particular, we get this behavior of tilt 0 dust in the limit. Another related result, or class of related results I wanted to mention, was that in some very special cases with even higher symmetry, there are some results for the Einstein-Vlasov system. This is due to David Dongo, Norbert Michigeme, and Taku. So these are actually mainly homogeneous and isotropic models of Bianchi type 1, and they were also able to get some global existence results in that case. Okay, so now I'm getting to my conclusions and outlook. So I can sum up in the following way. For lambda positive, the late time behavior is well understood in the homogeneous case. For lambda equals 0, much remains to be done. That should have become clear. I didn't mention lambda less than 0, but there's nothing interesting to do in this context, because for lambda less than 0, global existence always fails. So you always have a second singularity in case lambda less than 0. I mean, it's generally believed on the basis of astronomical observations that in our universe lambda is positive. So we're not too worried about lambda less than 0, although somehow the string theory is slightly like lambda less than 0. Not exactly sure of the argument. Okay, so an obvious question is what extensions to the inhomogeneous case are possible. I already mentioned one or two things in the case of a positive cosmological constant, and I'm sure more could be done there. In the case lambda equals 0, I think it's difficult. Now, all these results, I started off with a model which is initially expanding, and then I looked at its behavior as t tends to infinity. So it continues to expand forever. So maybe I should draw a picture of this. So if I draw, let's say, this is the volume of space as a function of time, and I start at some time t0, and the volume is increasing, and then it continues to increase in some way. So now, another question which we may ask if we think we already understand this expanding direction quite well, we can ask what happens in the opposite direction. What happens if we go in the past time direction? And it then turns out that if at least the cosmological constant is 0, you hit 0 after a finite time. So you get a singularity. So this is like the Big Bang singularity. So you do not get global existence in the past of this situation. So this is the question I'm asking here. What happens in the past time direction? And in this case, the time of existence is always finite for lambda equals 0. And for lambda positive, it may be finite, it may be infinite, it depends on the particular solution. Now, some things are known about the initial singularity in solutions of the Einstein-Vlasov system, but in general, they're very complicated oscillations, and people like to call these chaotic. I think there's a considerable amount of work which still has to be done to really make that precise, but this is the usual story. Chaotic oscillations. And in fact, it turns out that this is complicated even in the vacuum case. So I didn't emphasize this, but I can consider the case if I like f is identically 0, which implies that also the energy momentum tensor is identically 0. So that is by definition the vacuum Einstein equations, and there are lots of spatial dynamic solutions of the vacuum Einstein equations, and they can have quite complicated dynamics. In particular, they can show these complicated oscillations, which are allegedly chaotic. And in that context, I just wanted to mention that recently there have been advances in understanding this, understanding the way in which spatially homogeneous solutions of the vacuum Einstein equations behave near the initial singularity. And there's been major progress. I mean, after many years when there was lots of numerical stuff and lots of heuristic stuff, recently there's been major progress in really giving rigorous proofs of some aspects of the behavior near the initial singularity. And so this was, some of the people who have been working on this were Stefan Liebscher and collaborators, also François Béguin. And this is, I think, a really big difference from what I know from the past 20 years, let's say, what's happening now. And a reason for mentioning this here, I mean, of course, the vacuum case is a sub-case of Einstein-Vlasov, so we can't get rid of these cases. We must also consider them. But there are also things specific to Einstein-Vlasov which may be touched on by these results, or let's say where these techniques which these people have developed could also be applied to Einstein-Vlasov to different kinds of problems and to different kinds of oscillations. So it seems that there are certain kinds of oscillations when you approach the singularity which specifically have to do with Vlasov in the sense that you get pressure concentrating in certain directions. So they're very anisotropic. And this is the very last thing I wanted to say. These very complicated oscillations in the vacuum case are known under the name Mixmaster. And this Mixmaster paper was written in, I think, 1969 by Charles Misner. And in those days there was a special kind of food mixer around, I don't know if anybody knew it, called Mixmaster, and so he called this after the food mixer. I remember I saw one talk where somebody actually had a picture of one of these food mixers on the slides, but I haven't got this far. In any case, the thing that I wanted to point out was Misner was one of the first ones to discover this complicated oscillatory behavior, and the point is that this paper was on the vacuum case, but that wasn't his first paper on the subject. He also published a paper in 1967, and this was about collisionless matter and cosmology. And in modern language, this was a paper about Einstein-Vlasov. So this was really Einstein-Vlasov, and he discovered certain kinds of oscillations which are specific to the role of collisionless matter. This paper, by the way, is called The Isotropy of the Universe. Lovely general title. And Misner's idea, which didn't really pan out, was that these oscillations might be able to average out complicated behavior in the early universe and make things homogeneous. But in any case, I just wanted, so it's an interesting historical point that, in a sense, if you use the right language, Einstein-Vlasov and the complicated phenomena caused by Einstein-Vlasov was already active in 1967. Thank you.